Hello everyone. So this is Purba Mukherjee from the Center for Theoretical Physics, Jamia Millia Islamia. I'm working as a National Postdoctoral Fellow there, and today I'll be talking about a recent work which is the geometric determination of characteristic redshifts, hints for new expansion rate anomalies from DESI, BAO and DES supernovae observations. Our standard cosmological model, which is described by the 6-parameter Planck ΛCDM framework, can provide a good fit to a wide range of cosmological observations. But this is a phenomenological model which is described by the 6 fitting parameters, assuming that energy is given by a cosmological constant lambda, dark matter is cold, and a nearly scale invariant primordial power spectrum from inflation, and we can infer the derived parameters. One of the important parameters being the present rate of the cosmic evolution, that is the Hubble constant, and it can measure, the Planck observations can measure H0 very precisely. But we are all aware about the recent tensions and anomalies this Planck ΛCDM model is facing, the most significant being the Hubble constant tension, or the 5 sigma discrepancy in the measurement of the Hubble constant between early versus late time probes. To address this Hubble constant tension or these rising discrepancies, different dynamical dark energy models have been proposed, but we need to understand what happens if we deviate from ΛCDM. So instead of lambda, we have a dynamical dark energy behavior which is given by this equation of state parameter for dark energy, and the simplest model we can think of is the CPL parametrization, which has become very popular in literature. Also, this kind of a parametrization can be built from different scalar field theories. Now, if we look into the recent DESI results, so depending on the kind of supernova data we take into account, we notice that there is clearly an exclusion from lambda or ΛCDM by 2.5 to almost 4 sigma confidence level. Interestingly, if you look at the allowed region of the parameter space, we find that the W0WA parameter space is mostly confined in this quadrant, which denotes that the dark energy has an early phantom and a late non-phantom behavior, which has been shown in this plot for this equation of state parameter. So dark energy has an interesting phantom to non-phantom transition at later epochs. Now, it is very useful to understand whether these deviations actually indicate new physics beyond Planck ΛCDM, or these are merely artifacts of the kind of parametrization we are assuming. So let us begin with an expanding FLRW, spatially flat FLRW universe, where the dynamics is governed by the scale factor 80 universe. Now, to probe this universe, we use different distance measured. So we have something called the co-moving distance, which is given by this. The angular diameter distance and the luminosity distance are related to the co-moving distance by these expressions. Now, if we start from these Planck ΛCDM best field model, and if you look at the evolution of the different distances and their derivatives, we can identify 7 characteristic redshifts, or 7 distinct redshifts, where the distance and the derivatives have a crossing or an intersection. So these are denoted by these 7 redshifts, which are described, which can be obtained by these expressions. So at each of these redshifts, we find that the Hubble parameter can be exactly computed as a function of the cosmic distances and is independent of the derivative of these distances. So this allows us to infer the Hubble parameter at these 7 redshifts directly from supernovae and BAO observations. For the observational data, we are assuming the DES supernovae observations, which measures basically the distance modulus, which is related to the luminosity distances. We make use of the DESI-DR2 BAO data, which gives us measurements of the DMRT, DHRT, and the corresponding covariance matrix, where RT is the sound horizon at track epoch. We make use of the CMB angular scale horizon at recombination, and we impose this Gaussian prior on theta star, assuming that the early universe physics is consistent with Planck ΛCDM. For this exercise, we make use of two reconstruction techniques, multitask Gaussian process and knot-based spline interpolation. These are non-parametric smoothing techniques used to fit observational data to probe the underlying theoretical function directly from data, independent of any fiducial cosmological model. Dimensionless distance measures, which is given by this dx, where x can be either m for the co-moving distances, the a for the angular diameter distances, or l for the luminosity distances. So our job is to reconstruct these dm's, their first order derivatives and their second order derivatives, and we make use of the relations between the different distance measures to compute dA, dA prime, TL and TL prime. Now the characteristic redshifts are obtained by solving this equation, and we can determine each of these redshifts accurately by computing the distance and the distance derivative at the different redshift points through interpolation. To estimate the error at each crossing point, we need to determine the how the crossing is affected due to the uncertainties in the measurements in the reconstruction of dA and of the D and the D primes. And so we make use of these two relations to compute basically the crossing at the left and the crossing at the right of the redshifts. So we identify them as Zi left and Zi right, and the error associated to this redshift is given by sigma Zi. To compute the corresponding distance measures, once we accurately know Zi and ZL and Z right, we can determine the uncertainty using this relation. Now, after we have the estimate for this uncertainty and we have an estimate for the distances at each of these redshifts, we can compute the normalized Hubble parameter Ez. So Ez can be written as a function of dA from here and a function which is dependent on the redshifts. So for each of these Zi's, we can propagate the uncertainty in Ezi by the standard error propagation, where a part comes from the error in dA and a part comes from the error or the uncertainty in the redshifts. So these are the plots. So in the upper panel, we have shown plots for the co-moving distances, this first derivative and the second derivative. So this is with the multitask Gaussian process regression, and here we have shown the results with the rational quadratic kernel. We can use different other kernels which have been tested in our work. Here we have shown the estimates for the characteristic redshifts and their uncertainties that we have obtained. This plot shows how the reduced Hubble parameter, the errors in the reduced Hubble parameter scale. So we show the contribution from the error in dA, the contribution for the error in Z's, and then we show the total contribution to the total error. Now once we have identified these 7 characteristic redshifts, we consider them as knots which are fixed, and we do an interpolation about these knots. So here we are considering basically knot-based spline reconstruction, and we do the same exercise, and these are the results. So in both the cases, we see the results are mostly consistent within 2 sigma. Interestingly, we find that in both dm and dm prime and dm double prime, we see that the reconstruction result that is shown in blue has a clear deviation from Planck ΛCDM at the low redshifts. We also notice that there is a changing slope for dm double prime at very low redshifts. Here the results have been shown for spline interpolation order of K4. We have done for orders 3 and 5, and the results are mostly similar. And these are the results. So in this table, we have shown the reconstructed values for dA and Ez at the characteristic redshift Zi. So we have compared each of these results with the corresponding Planck ΛCDM estimates, and we have computed the tension between these two values. So these are the different redshifts, characteristic redshifts. These are the uncertainties associated to those points which are dependent on the reconstructed 1 sigma bands of the cosmic distance and their derivatives. This is the estimate for the dA along with the errors, And this is the estimate, the Planck 2018 best fit values, and this is the corresponding tension between them. So once we know dA and the Zi and their uncertainties, we can compute EZi from them directly, and we can compare it to the best fit Planck ΛCDM value, and we can also compute the tension between them. So we notice a clear trend that in the very low redshifts for around 0.35 to 0.7, we see that there is almost a 4 to 5 sigma tension in the estimates of these expansion rate, so which we are calling as new expansion rate anomalies from the DESI and the DES supernovae observations. And this tension is consistent across both the reconstruction frameworks and also the choice of the kernel we are assuming for doing the reconstruction, or the order of spline we are taking to do the interpolation in the knot-based reconstruction. At higher redshifts, so we see that so much as the tension is not very significant. That is, at higher redshifts, we find that the results are consistent with Planck ΛCDM. Now we plot the reconstructed expansion history of the universe, and these are the plots. So in the upper panel we have plot Ez scaled with respect to 1 plus z and q of z, which is basically the deceleration parameter. So we also notice a clear region where our reconstruction shown in blue deviates from Planck ΛCDM at the very low redshift intervals, but at higher redshifts we see that these coincide very nicely within the 2 sigma. When we do the plot for the Ez versus 1 plus z, Ez by 1 plus z with respect to redshift, we notice that there is a change in this slope, and this where our reconstruction shows that the Planck ΛCDM has a greater dip compared to our reconstruction. Now this minima points to the region where the universe undergoes a decelerated transition from a decelerated expansion to an accelerated expansion, and this is very consistent to what we find in the plot for the deceleration parameter. But we notice that at higher redshifts, the evolutionary history, although consistent with Planck ΛCDM, at the later time we find that there is a clear deviation from Planck ΛCDM at more than 2 sigma. Also, we also notice a slowing down of the cosmic acceleration at these very low redshift regions irrespective. Next, we plot the behavior of the dark energy density to show the evolution of the energy density rho dE and the pressure PdE and their total sum, which basically describes the null energy condition. The pressure can be reconstructed from E and E prime directly without any further input, so it's more robust. However, for the energy density, we require an additional input from the omega matter, for which we adopt the Planck ΛCDM prior on omega mh square, to be calibrated using early universe physics. So we find that for both the pressure and the energy density, the result shows a clear deviation from the Planck ΛCDM. For the energy density, we find that the value of rho dE slightly increases, and then it becomes consistent with Planck ΛCDM within the 2 sigma. For the PdE, at very low redshifts lesser than 0.3 and around 1, we notice 2 regions where the pressure shows a deviation from the constant lambda, and these 2 behaviors clearly signal for the presence of a dynamical dark energy component. Next, we analyze the redshift evolution of this quantity rho dE plus PdE. So we find that for z less than 0.7, we see that this quantity is always positive. That means that there is no violation of the null energy condition in this redshift region. For higher redshifts, we notice that the mean curve shows a dip to negative values. However, there is always a allowed region within the 2 sigma parameter space where the null energy condition holds. This means that in contrast to the DESI results, which shows a violation of the null energy condition with the CPL parameterization. That is, we needed an early phantom behavior to explain the data. This is not the case here. Again, we plot the dominant energy condition, which is given by this quantity, and this also shows similar features. At very low redshifts, we see that this quantity always remains positive, that is, the dominant energy conditions always holds true. For higher redshifts, when we see that the dominant energy condition holds true within the 2 sigma confidence interval. So we find that there is a validity, the results show validity of the null energy and the weak energy condition and the dominant energy condition. So that means that our results show although there is a deviation from this Planck ΛCDM behavior, the dynamical dark energy behavior can easily be modeled by scalar field theories, which have this where the energy conditions holds true. So to summarize, in this work we have done a model independent reconstruction of the late time evolution of the universe, assuming there is no new physics in the decoupling era. We focus on the determination of 7 characteristic redshift points using the properties of different distances and their derivatives in a spatially flat FLRW universe. We make use of 2 reconstruction frameworks, the multitask Gaussian process versus the knot-based spline interpolation. We test for different kernels and different spline orders, and we cross-check that our results are always consistent throughout these different frameworks. For all the cases, we observe that the tensions are appearing at the lower redshifts with Planck ΛCDM estimates, particularly in EZ around 4 sigma, the knot-based spline algorithm. For higher redshifts Z greater than 0.7, the reconstructed estimates are again consistent with the Planck ΛCDM predictions. The reconstructed pressure for dark energy shows a clear departure from Planck ΛCDM at more than 2 sigma confidence level, and the dark energy density always remains positive but shows a departure from a constant lambda behavior at more than 2 sigma confidence level at low redshifts. If we look at the allowed regions of the dark energy evolution, we find that the dark energy behavior within 2 sigma always includes the validity of the null energy, the weak energy and the dominant energy condition, and showing that we do not need to go beyond canonical scalar field theories to model this dark energy sector, and we do not need early phantom-like behavior for dark energy.